So terrestrial laser scanner point clouds. If you take a look at the floor objects here, and you look at the histogram, you're going to see something like this. If you take a look at the peak of the histogram itself, it's around 3 millimeters there, which is consistent with the amount of random measurement error that you get in the instrument. BLK2GO, this one I got it from the Leica website. This one, if you take a look at it, is 5 millimeters. So a bit more. The fact that it's 5 millimeters is more or less consistent with reality. You know, we're not expecting the handheld laser scanner that is mobile to actually be as accurate as your terrestrial laser scanner, right? Fast forward to if I wanted to do it with an iPhone X, and this is more consistent with what it is. You have different types of peaks. Why do you have these? Because every time that it's doing the stitching, there's some errors associated with that, right? So it is having those errors as well. And if you take a look at it, this is around 2 centimeters. So how do we incorporate uncertainty? Well, there are some measures that you would be able to do, and we call it error ellipsoid. What does this mean? This means that for every point, there's an uncertainty associated with it that comes from various sources. That uncertainty that is associated with that particular point comes from the random measurement error, okay? It comes from registration error, and it comes from various different other aspects as well. That is going to be the sigma in the middle that you're going to be observing here. That's what we call the covariance matrix. That covariance matrix would tell us how large this ellipsoid is going to be, right? In this direction or in this direction or in what direction? Is it a sphere? Is it an ellipse? What is it? Ellipsoid, what is it, right? That's what that covariance matrix is going to provide. And then the xi is basically your center. So for every point, you're basically going to be getting that there, right? From that area. And then that would be the center. And then it gets enlarged there. And then here you have a probability there. That is the chi-square distribution with probability P and degree of freedom alpha. Degree of freedom is basically the dimensions of your data. In this case, it's 3-dimensional, so the alpha is going to be 3. P is going to be your confidence level. So it's going to be 95%, 97.5%. What is going to be the confidence that you're going to want? That would be dictating exactly how much the semi-major and the semi-minor axes are going to be. So the directions of these would be provided by the eigenvalue analysis of the covariance matrix. This is exactly, if you remember, our principal component analysis. The lengths of these would be determined by means of our chi-squared distribution. From that, we know more or less how much, dependent upon the standard deviations that we have from each and every one of the areas, how large this error ellipsoid is going to be with respect to a particular amount of probability. If we want 95% probability is, let's say, this much, 97% is a bit larger. That means that it would encompass all points that are randomly sampled from a multivariate normal distribution with standard deviation, with covariance sigma and mean of xi. That's what this means. Once we have these ellipsoids, then we would be able to see whether that particular surface is within that ellipsoid as well or not. So let's say if I want to say there's a correspondence between a point and the surface. That point could be anywhere inside of this ellipsoid. Then if these two are going to collide or have some sort of intersection, we can say that this point has some probability of intersecting with this surface. As long as they intersect, we can say that they belong together. Same with a cylindrical surface or a curved surface, it's going to be the same. It doesn't matter. As long as that surface intersects with that particular error ellipsoid, there is a possibility that is going to be inside of it.